Hello everybody, it is my pleasure to present the work on current voltage characteristic simulation of organic solar cells using discontinuous Galerkin method by authors myself Nataša Ćirović and my colleagues Ali Kalf, Jovana Gojanović, Petar Matavulj and Sandra Živanović. This work is done in cooperation of Institute for Micromanufacturing, Louisiana Tech University, USA, that conducted the fabrication and testing of organic solar cells, and School of Electrical Engineering, University of Belgrade, that conducted modeling of JV characteristics. I will introduce you to the instability problem that occurs when modeling the current voltage characteristics of organic solar cells, with oftenly used model when the full boundary conditions are applied. The methodology that we use is development of novel numerical approach for achieving improvements in stabilization when full boundary conditions are applied in the model. The results are obtained on the simplified standard drift-diffusion model equation system and will be compared with existing numerical methods on such simplified model in the results and discussion section. As a conclusion, this now numerical approach shows less sensitivity to the form of boundary conditions, and in future work we will try to improve this method by implementing Schaffeter-Gummel numerical flux. In the steady-state drift-diffusion model, shortly DDM, of organic solar cells, the Dirichlet boundary conditions on the entire boundary is most often incorporated, or Neumann boundary condition is added to a part of the boundary. The recommended numerical approach for DDM is based on Voronoi finite value method using generalized Schaffeter-Gummel shortly SG flux. In one-dimensional case, this approach is reduced to finite difference SG discretization scheme, shortly DDM FDSG. It was shown that the surface recombination have a significant impact to the performance of organic solar cells, and it is incorporated in DDM through the boundary conditions of Robin type. Under these boundary conditions, DDM FDSG shows certain instabilities. In order to investigate the surface recombination influence on OSC JV characteristics, a model stable for all surface recombination velocities values of holes and electrons on both contacts is required. We start with the steady-state drift-diffusion model, which consists of Poisson equation 1, continuity equations for electrons and holes 2 and 3, and drift diffusion expressions for electron and hole current densities, equations 4 and 5. Here are shown the symbols and quantities from the DDM model from the previous slide. We can see the simplified schematics here of OSC with ethos anode and aluminum cathode and organic active layer in between. Boundary conditions for electrostatic potential and hole and electron densities are given in both contacts, x equals 0 and x equals d. D here is the length of the active layer. By inserting the drift diffusion expressions for Jn and Jp, shown previously in equations 4 and 5, in boundary conditions for hole and electron densities, these boundary conditions become of Robin type. Also, the surface recombination velocities, namely SNA, SPA, SNC, and SPC, have a significant role in these boundary conditions. Here the symbols and quantities from the boundary conditions are presented. SRV for electrons and holes on both electrodes, anode and cathode, namely SNA, SNC, SPA, and SPC, can take any value from -infinity to +infinity, which gives infinite number of solutions. In order to systemize the outcome, we define three main SRV categories compared to the average drift velocity of considered charge carriers, holes, or electrons. The average drift velocity for charge carriers was chosen as quantifying parameter because drift component of current density is taken to be dominant. When SRV is at least one order of magnitude less than average drift velocity, it is categorized as small, and it defines blocking contacts. When it is the same order of magnitude as the average drift velocity, it is categorized as medium, and it defines contact that is neither blocking nor conductive. and when SRV is at least one order of magnitude larger than average drift velocity, it is categorized as large and it defines conductive contact. Since the considered model consists of three coupled second-order nonlinear non-homogeneous differential equations, we introduce certain simplifications in the model. First, we assume the electric field to be constant. Second, to enable separate analysis of the effect of electron and hole boundary conditions on the steady-state solution, the electron and hole continuity equations were decoupled by taking the hole's bimolecular recombination velocity to be Rp gamma times p square, and analogically for electrons Rn equals gamma n square, where gamma is Langevin recombination constant and n and p are electron and hole densities respectively. In this way, the system is reduced to two separate second-order nonlinear non-homogeneous differential equations, one for holes and the other for electrons. The discretization of the system of equations is done by using the finite difference method, including Schaffeter and Gummel SG approach. SG uses exponential approximation of carrier densities at midpoints of one-dimensional mesh. The Newton method is used for solving algebraic system of equations, and the model shows a significant instability when SNC and SPA take small values. Another approach for solving the simplified model was DDM-DG, in which the discontinuous Galerkin method was used. To solve the simplified model consisting of one nonlinear second-order differential equation, Hore-All-Electron continuity equation, we first decouple the equation to obtain a system of two first-order equations by introducing the auxiliary functions r and g respectively. Discontinuous Galerkin was applied to each system of nonlinear first-order differential equations. It is a hybrid method that combines the advantages of finite volume and finite element method, using local high-order expansions to approximate the unknowns to be solved for. Each expansion is defined on a single mesh element. In 1D, it is a subinterval, and it is connected to other expansion defined on the neighboring element via numerical flux. For expansion of the solution, we used a local DG scheme with Lagrange polynomials of degree 8 at Legendre-Gauss-Lobato nodes as testing functions and discrete inner product to achieve the weak formulation of the problem. The interval is divided by nodes xk into subinterval ik, which is defined by xk plus 1, and the solving algorithm is similar to standard finite element method, but results in discontinuous solution, thus providing two values in each node, one inside the subinterval ik denoted with minus and the other outside denoted with plus. Having two values in each inner node requires introduction of a numerical flux, which is a function which handles the two values in a way that reflects the physics between two neighboring subintervals. The Lux-Friedrichs numerical flux for the drift term and the local DG flux for the diffusion term were used. In boundary nodes, the boundary conditions were applied. Here the equations for electrons are presented and the ones for holes are analogous. The DDM FDSG simulations were done for holes and electrons. The orientation of x-axis for hole and electron calculations is the same, as it can be seen here in figures 3 and 4. Three types of boundary conditions are considered: Dirichlet, mixed 1, and mixed 2 boundary conditions. When large value of SRV is applied on a certain contact, BCs on that contact reduce to Dirichlet type. Otherwise, when medium or small value is assigned to SRV, BCs keep the Robin form. In order to define the SRV combinations that correspond to mixed 1 or mixed 2 boundary conditions for holes and electrons, it should be known that holes and majority carrier are majority carriers on anode and minority on cathode. For electrons, it is opposite. They are majority carriers on cathode and minority on anode. The hole and electron SRV combinations for obtaining each type of boundary conditions are presented in tables 3 and 4 for holes and electrons respectively. The calculations for DDM-DG were the same as for DDM FDSG, except that the orientation of x-axis is not the same as it can be seen from figures 5 and 6. Figure 7 shows the JNV and JPV curves obtained for Dirichlet boundary conditions and for mixed 1 boundary conditions when SRVs for minority carriers are set to medium values. The voltage values are set on the abscissa. In the upper graph, the electron current density Jn is set on the ordinate. The curve values are calculated for both models DDM FDSG and DDM DG for Dirichlet boundary conditions marked in black curves and for mixed 1 boundary conditions marked in red curves as shown in the legend. In the lower graph, the whole current density Jp is set on the ordinate, and as above, the current values are calculated for both models and both types of boundary conditions, Dirichlet marked in black curves and mixed 1 boundary conditions marked in red curves. For Dirichlet and mixed 1 boundary conditions, both models gave nearly the same prediction of JNV and JPV characteristics. In this case, the calculations were stable for DDM FDSG model in the wide range of SRVs. Figure 8 shows the JNV and JPV curves obtained for mixed 2 boundary conditions when SRVs for majority carriers are set to medium values. In the upper graph, the electron current density Jn curve for DDM FDSG and DDM DG are shown in black and in red line respectively, both with mixed 2 boundary conditions. Similarly, in the lower graph, the whole current density JP curves are shown for both models with mixed 2 boundary conditions. For M values of JNV and JPV curves predicted by the DDM FDSG model are unexpectedly large in the first quadrant. The DG model, in the case of fixed 2 boundary condition with M SRV values, gives S-shaped JNV and JPV curves as expected when the surface recombination becomes significant in the device. Figure 9, previously to the previous one, shows the JNV and JPV curves obtained for mixed 2 boundary conditions, but now when SRVs for majority carriers are set to small values. For mixed 2 boundary conditions with S SRV values, the DDM FDSG calculation manifests high instabilities and gives broken JNV and JPV curves. The DDM DG model, in the case of mixed 2 boundary conditions, is stable for S SRV values, and again calculated JV curves show S-shaped deviation. Figure 10 shows the JV curves calculated by Jn plus Jp obtained for the DDM DG model with Dirichlet boundary conditions in red line and the measured JV characteristics in black empty circle line. The experimental results are achieved for the PEDOT PSS P3HT PCBM AL solar cell, and the schematics of the device is presented on the figure as well. The agreement between the calculated and experimentally obtained JV curves is very well, which validates our model. Here in this table, we see the fabrication parameters of the experimental device. To conclude, there is an evident problem with the DDM FDSG model when Robin boundary conditions are applied. The strong instabilities are apparent when SRV for majority carriers are reduced. The suggested approach to overcome the instabilities in this case is the DDM-DG model developed in this work. The DG method showed better stability in the case when majority carriers SRVs were reduced. We have noticed that the sign of SRVs has strong influence on the calculation stability in both DDM, FDSG, and DDM, DG case. This issue needs further research. Also, for further research, we want to include implementing Schaffeter-Gummel numerical flux in the DDM-DG model to check if it would make some additional stability improvements. Thank you for your attention, and We are expecting your questions. All the best.